Hey, hello everyone. Is everyone able to hear me?
Yes.
Yes.
Okay, great. So in this tutorial, we will be covering exercise 5.2 and exercise 5.3. I hope you have already covered this in the lectures. So in exercise 5.2, we have the exercises 5.2.4 and 5.2.5. So we have decided to drop these two exercises from exercise 5.2, but the rest of the material is actually covered in 5.2. So only 5.2.4 and 5.2.5 is not covered. Okay, so let's go ahead and start with our first question from 5.2. Okay, is everyone able to see my screen?
Yes.
Yes.
Okay, great. So as mentioned earlier, so we are excluding exercise 5.2.4 and 5.2.5 from 5.2. So this is on page number 362 of your textbook, and this is going to be the first question. So this question is regarding the strong induction. Okay, so this first question here, so we are supposed to use strong induction to show if you can run 1 mile or 2 miles, and if you can always run 2 more miles once you have run a specified number of miles, and you can run any number of miles. So again, just like as in the previous tutorials we have been doing and proving using the induction. So here, strong induction is no different. Strong induction is just as the name indicates, it's a stronger proof of induction. And you will see that in a minute. So here, just like the normal induction, we will have the basic step and the inductive step. So in the basic step, what we have is basic step. So we are told that we can run 1 mile. So here our t of 1 be the function which represents that we can run 1 mile. So here 1 indicates the number of miles we can run. So p of 1, we are representing the number of miles. So here, let me just say this, p of n here represents the number of the n number of miles run. Okay, so now based on that, we did the basic step. Based on that, we did the basic step, and we know that we can run 1 mile from the question. So we know that our basic step is true. So let's move on to the inductive step. So we assume the inductive hypothesis that we can run any number of miles from 1 to k, from 1 to k. So therefore, so this is our inductive hypothesis that we can run any number of miles from 1 to k. Okay, now we must show that we can run k plus 1 miles, right? So this is how the induction is. right? So we assume that P of n or P of k is true, and then we try to prove that it's also true for the one step ahead. So here, one step ahead is the k plus 1 mile. We have to prove that. Now, if k equals to 1, then we are already told that we can run 2 miles. So if k is greater than 1, then the inductive hypothesis tells us that we can run k minus 1 miles. So therefore, we can run k minus 1 plus 2, which is basically equals to k plus 1 miles, which is our inductive hypothesis. And therefore, inductive step is true. Now, because our both basic step and the inductive step is true, therefore we have proved it. Basically, what we did here is, so we have this question here which tells us that if you can run 1 mile or 2 miles, to show that if you can run 1 mile or 2 miles, then if you can always run 2 more miles once you have run a specified number of miles, then you can run any number of miles. So here we said in the question it says that we can run 1 mile, therefore we have this, so P1 is true. So inductive, so basic step is true here. And then in the inductive step, what we do is we assume this P, so we assume this P of n, we don't say P of n here in the inductive step, we replace it with some k variable. And then we assume that P of k is true, and we try to prove that it's also true for P of k plus 1. So if we prove that it's also true for P of k plus 1, then it's true for any P of k. Therefore, it's true for everything, and hence that is the solution. So in the inductive side, what we did is that we assume the inductive hypothesis, which basically is mentioned here, that we can run any number of miles from 1 to k. And then we must show that we can run k plus 1 miles, so which is what I write here. We try to prove that. And then here, if k equals to 1, right? If k is equals to 1, so then from the basic step, we already know that this is true, so we can run those miles. And if k is greater than 1, right, then the inductive hypothesis tells us that we can run k minus 1 miles. So therefore, we can run k minus 1 here plus 2, which is basically equals to k plus 1 miles, right? Which is over here from our inductive hypothesis. And therefore, we know that this inductive step is true. Therefore, we have proved this. Okay, so this is the proof for this question. Let's take another question. So in question number 5 here, so we are supposed to determine which amounts of postage can be formed using just 4-cent and 11-cent stamps. Okay. So here we have this part number A. So here we have which amounts of postage we have. So we have 4-cent stamps, and then we have 11-cent stamp, and then we want to know which amount of postage can be formed. So this is 4, right? So we will try to enumerate most of them. So here we have this 4-cent stamp. So definitely we can have the 4 amount of stamp postage. So 4, and then the 4 multiple is 8 as well. So therefore 8, and then we have this 11 because we have the 11-cent stamps as well. So 11, and then we have 12 because 12 is divisible by 4 as well. Basically, what this means is all the multiples of 4 and all the multiples of 11. So 11, 12, and then we have also 15, which is basically 11 plus 4. So we have to try to come up with all the possible numbers we can make with 4 and 11. Okay. 15, likewise, we can do 16 because it's divisible by 4. 19 because you can add 4 to 15, and then you can make 19. Likewise, 20, 22, 23, 24, 26, 27, 28, and all values 32, and all values greater than 30. Okay, and now we have enumerated those. Now we have to prove that using the principle of mathematical induction. Be sure to state explicitly your inductive hypothesis in the inductive step. So now we have to prove this. So we will say, let's, just like any other proof, we suppose P of n represents something because P of n represents some function, and that makes our proof easier. So let P of n be the statement that we can form n cents of postage using just 4-cent and 11-cent stamps. Okay, so here we have defined the definition for P of n, which basically represents that n cents of postage we can represent using just 4-cent and 11-cent stamps. Okay, so this is what our P of n represents. Okay, so we want to, what do we want? We want to prove that P of n is true for all n greater than or equal to 30. Now, basic step. Okay. So here we have, so in order to prove that, so we have to prove n is less than or equal to 30, and then we have this P of n, which represents basically the n cents of postage using just 4-cent and 11-cent stamps. So in the basic step, our smallest one here therefore is 30 because we are saying n is greater than or equals to 30 using this assumption, right? So we want to prove that Pn is true for all. So in the basic step, as we already know, that we start with the smallest number in the domain, which is 30 here. So we will start with 30, and then we will say here that 30 equals to, how can we make 30? We can make 30 using the 2 11 stamps and then 2 4-cent stamps. Okay, so this one here makes 30 amount of postage using 2 4-cent stamps and 2 11-cent stamps. So therefore, our basic step is true. Now we move to the inductive step. In the inductive step, we will have an inductive hypothesis. And our hypothesis is assume that we can form k-cents of postage and we will show how to form k plus 1 cents of postage So now we will do the inductive step. So here, if the k-cent included an 11-cent stamp, then replace it by 3 4-cent stamp, right? Because if it's k-cent has an 11-cent stamp and then we want to prove it for k plus 1, right? And if we have 3 4-cent stamps, which will be 12, right? So 11, and then we have 4-cent stamps, 3 4-cent stamps, which is equals to 12, right? So here 11 is our k, and then this one is our k plus 1. This one is our k plus 1. So this one here proves that it's true for k plus 1. Now, otherwise, k-cents was formed from just 4-cent stamps. Right? So if k-cents basically has 11-cent stamp, then we will just replace it with 3 4-cent stamp to get the k plus 1. And if it doesn't have the 11-cent stamp, so we will k-cent was formed just using 4-cent stamps, because that's the other possibility. Because k here is greater than or equal to 30, there must be at least 8 4-cent stamps involved so we replace 8 4-cent stamps by 3 11-cent stamps, and we have formed k plus 1 cents in postage. So this is the inductive step. So here, what we are saying is, so we have k cents of postage. And then what we are trying to prove here is that we can form any number of postage using k plus 1 cents as well. So we assume that in the k cents, we have 11-cent stamp, at least one 11-cent stamp. Then if we replace that 11-cent stamp by 3 4-cent stamps, then we have already, so here we have formed k plus 1 cents in postage. Okay, we have, it's only when, so let me write down here, case 1, when the k cents include 11-cent stamps. So this is the case 1. Case 2 is when k cents doesn't include 11-cent stamps, or in other words, it only includes 4-cent stamps.
Oh, the k plus 1 is correct, because if you replace, for example, case 1, we had 11 cents because there were 4 cents remaining, because we multiplied 4 cents by 3, it gave us 12, which is k plus 1. Is that why it is correct?
Exactly.
Oh, okay.
Yeah. So what we are trying to prove is, we are assuming that it has, so k cents, right? So we can only form the k cents using 11-cent or 4-cent stamps, right? So we divided that into 2 cases. So first case is, so we assume that, let's say that it has one 11-cent stamp. And then in that case, we try to prove it for k plus 1, right? So here, 11 cent here, if we replace this, because if it has 11 cent, and if we replace this with 3 4-cent stamps, then it will be 12, which is already k plus 1 cent. So therefore, we have proved that inductive step in this case. And then the other case is when it doesn't have any 11-cent stamp, it only has 4-cent stamps, right? So in that case, what we do is, so here we said, because its k is greater than equals to 30, right? So because here in this assumption, we assume that n is greater than equals to 30, right? So here, because k is greater than equals to 30, so let's assume that here we have at least 8 4-cent stamps, right? Which will be 32, right? Now, if we replace this with 3 11-cent stamps, it will be 33, which is k plus 1, right?
Oh,
So therefore, we have proved that in this step as well. Questions?
Oh, sorry.
Yes. Any questions?
Sorry, was this mathematical induction or strong induction? The one you used to.
All right. So here, let me just pull up the definition for the induction versus strong induction to just make it a little clearer. So one of you guys were asking if this is strong induction or the weak induction. So this one here, if we read the question here, so it says that prove, so this one is just the normal induction. The next part C is basically using the strong induction. So in the normal induction, which is also called the weak induction, so the only difference appears in the inductive hypothesis step. So where we assume in the inductive step, the assumption in the inductive step is basically in the inductive hypothesis. So that's where the difference lies. So in weak induction, we only assume that a particular statement holds at the kth step. While in strong induction, we assume that the particular statement holds at all the steps from the base case to the kth step. So we will see an example of strong induction now. Okay. So here we did this step using the weak induction, and now we will be moving forward to the C part, which is basically using the strong induction. So let's do that C part here. Okay. So here we have the same Pn. So we will just copy this. The definition of the Pn is just the same, which is that Pn will be the statement that we can form n cents of postage using just 4-cent and 11-cent stamps. And what we want to prove is just the statement of Pn. Now to prove that Pn is true.
Miss, can we make n any number? Like, can n be, like, instead of 30, can we use another number? Or we should use 30 for this case?
In this case, we use 30 because we are assuming that here. So in the A part, so we are asked, right? So which amount of postage can be formed using just 4-cent and 11-cent? So we have this, right? So we know that this one we can actually verify, right? So for example, if I have 30, right, the number 30, I can make it using 11 cents and 4-cent stamps as well. So let's say I can take two 11-cent stamps and two 4-cent stamps and make the number 30. So this one we can actually prove. But in order to prove that all values greater than 30, right? So we are basically proving that step, right? Right. So what is that really true? Like we can form for example, for 31, right? Can we, and can be any number, but just for the sake of proof, right? We are actually saying in that way that it can be n, and can be any number which is greater than or equal to 30, right? So just to prove that it can be any number greater than 30, so we are doing the inductive hypothesis on here. And therefore we have done the basic step and inductive step using the weak induction, and we found out that it was actually true that we can form any number greater than or equal to 30 using 4-cent and 11-cent stamps.
But we can use, wait, that means we can use any number other than 30. We can use 28, right?
Yeah, but we are trying to prove for all the numbers greater than 30.
For all the numbers. Okay.
Yes.
Okay, I guess, yeah.
Right, that's why. So now, so to prove that Pn is true for all and greater than equal to 30, we check for basis step that 30 equals to 11 plus 11 plus 4 plus 4, right? So this is how we make 30 using the 11 cents and 4 cents stamp. Likewise, I can make 31 using 11 and 5 4-cent stamps. So 4 plus 4 plus 4, 4 plus 4 plus 4. So this will make 31. Likewise, I can make 32 as well. And then I can make 33. And in fact, I can make any number greater than or equal to 30 using 11 and 4-cent stamps, right? Therefore, for the inductive step, assume the inductive hypothesis that P of J is true for all J with 30 is less than equals to J is less than equals to K. So this is basically the main part, the difference between strong and weak induction. We don't have that strict or strong kind of inductive hypothesis in the weak induction here. So we only assume that we can form K cents of postage. We will show how to form K plus 1 cents of postage there. But here in this step, we are having a very strong hypothesis or a strong induction here. So what we're trying to say here is that Pj is true for all j with this limit of k and between k and 30. So where basically k is an arbitrary, it could be any number slash integer, because integers are numbers in mathematical terms, greater than or equal to 30. So we want to show that P of k plus 1 is true, just like we did in the previous one. So because we know k minus 3 here, k minus 3 is greater than equals to 30. So we know that P of k minus 3 is true. That is that we can form k minus 3 cents of postage. So if we put one more 4-cent stamp on the envelope, and we have formed k minus 3 cents of postage. Oh, sorry, k plus 1 cents of postage. In this proof, our inductive hypothesis was that P of J was true for all values of J between 30 and K inclusive, rather than just that P of 30 was true. Okay, so this is how we do the strong induction. Strong induction, basically what we do is the difference is in the inductive hypothesis step. So it's a little more stronger hypothesis, and we try to prove whatever we our hypothesis in the inductive step. So here we have this same thing. We're trying to prove P of K plus 1 is true. We're trying to prove here. So because here K minus 3 is greater than equals to 3, we know that P of K minus 3 is true. So we are basically doing the same thing, but here previously what we did here is here in the previous lecture, in the previous part B, what we did here is we have this K plus 1 here, so which was starting from P of 30, but now here we are starting from P of 33, right? So equal where K is unequal, or yeah. So this is how you do the strong induction. This question is getting a little longer, probably taking a little more time. So probably next question might make a little more sense. Now that we have some idea of strong induction, so let's move on to the next question. So this is the question number 9. So using strong induction, we have to prove that square root of 2 is irrational. And then there is some hint that let Pn be the statement that square root of 2 is not equal to n over b for any positive integer b. So let's P of n, okay, P of n be the statement that there is no positive integer b such that square root of 2, so I'll just say square root of 2, it's just represent this here, square root of 2, okay? The square root of 2 equals to n over b. Okay, so this Pn represents that the square root of 2 is equals to that there is no positive integer b such that square root of 2 is equals to n over b. Okay, so this is what it represents, P of n. So we do the basic step. In the basic step, we have P of 1 is true. Why it's true? Because if we take square root of 2 is greater than 1 is greater than or equal to 1 over b, right? Because square root of 2 is around 1.44 something. So here, because it's greater than 1 and it's greater than 1 over b, therefore this basic step here is true. Now, we move towards the inductive step. Now in the inductive step, we have the inductive hypothesis. So in the inductive hypothesis, we say assume that P of J is true for all j less than or equals to k, where k is an arbitrary positive integer. So we prove that we need to prove that p of k plus 1 is true by contradiction. So assume that square root of 2 equals to k plus 1 over b. Okay. For some positive integer b, then 2b square equals to k plus 1 square, k plus 1 square. So because 2b square is equals to k plus 1 square, and we know that k plus 1 square is positive. I'm sorry, positive even. Okay. And hence k plus 1 is even, because even if it's odd, you add 1 to it, it becomes even because of that reason.
Miss, why did you change it to k plus 1 square?
So because here we are saying that we assume that square root of 2, right, is equals to k plus 1 over b, because we want to prove this, right, on inductive step, just like in the inductive hypothesis, right? We have this, we're trying to make it that way, right? So just to remove that square root, right? So we're just trying to simplify it. Okay.
Yeah.
So it is like this, right? So square root of 2, and then we have this here. Maybe I can just copy this. It's like this, right? Square root of 2 is equals to k plus 1. Now, if I want to remove that square root, I will have to take the squares on both sides, right? So if I remove this square, that square root cancels the square, so it will be, and then it will be k plus 1 square here, then divide by b square. Now this b square, it actually gets multiplied here. So it becomes 2b square. 2b square here, which is equals to k plus 1 over square, right? Which is over here. Okay.
I get it now.
Okay, you got it? Okay, great. So just basically just trying to reword what's in the assumption. Okay, so we have this. So because it will be k plus 1 will be a positive even because it's square, right? And therefore k plus 1 is even. Now moving on. So write k plus 1 equals to 2p for some positive integer t means 2b squared equals 4t squared. 4t squared and b squared equals to 2t squared. By the same reasoning as before, b is even. So b equals to 2s for some positive integer s, then square root of 2 equals to k plus 1 divided by b equals to 2t divided by 2s, which is equals to t res. But t here, you know, the t is less than or equals to k. So this contradicts the inductive hypothesis and our proof of the inductive step is complete. Okay, basically, so what we did here is, so we have the statement Pn, right, which represents this square root rho equals to n over b, and then it says that there is no positive integer b for such thing, right? So we start with no positive integer, right? So no positive integer, we start with the smallest one. So here P1 is the smallest one in the domain. We check for the basis step here, and then we find out that this is true. It's true. And then we move to the inductive step here. So in the inductive step, what we did is just like we do. So we have that assumption Pj or P of n, but just replacing n with j. But it represents the same thing. So it is true for all j less than equals to k, where k is an arbitrary positive number. And then we have to prove that p of k plus 1 is true by contradiction. Now, so we are proving this using contradiction, because here we are trying to prove that there is no positive integer b such that this is true, right? So when the question is of the shape like this, so we try to prove it using contradiction, because contradiction, what it does, it assumes that something is true, and then later during the proof we find out that it's not true. Therefore our assumption that it's true is false. Therefore we know that this is wrong. Therefore it proves that this is true. Okay, so here we assume that this is true for some k, right? For some k positive integer k, for some positive integer b, and then later on we did the proof, and then we find out that t is less than equals to k. So therefore this assumption that we find out that it's true, so it contradicts our inductive hypothesis. This is which is the inductive hypothesis here. So it contradicts that hypothesis, the assumption. So therefore we know that this is not true, and hence because we know that this is not true, so our assumption must be true. So this is how we do the contradiction in inductive step as well. This is one of the ways that you can try to prove it, but there are other ways like using direct proof as well. You can probably try that, but that might not be very fitting in this example, as we're trying to prove that there is no positive integer. If the question is something like prove that is true for all positive integers, probably we can go with that. But when it's worded like there is no positive integer, then we can try to prove it using contradiction. Okay, let's move on to the next question. We'll have a lot more to cover. So in the next question, so we have this here. So we have a jigsaw puzzle is put together by successively joining pieces that fit together into blocks. A move is made each time a piece is added to a block, or when two blocks are joined. Use strong induction to prove that no matter how the moves are carried out, exactly n-1 moves on are required to assemble a puzzle with n pieces. Okay, so just like with any other proof, we start with defining what our Pn represents. So Pn be the statement that exactly n-1 moves are required to assemble a puzzle with n pieces. So this is our Pn. We do the basic step. And then the basic step, we have the smallest one is n is 1, because the smallest move is 1 move, right? So we will take P of 1. So P of 1, we know that is trivially true, because 1 is the smallest, because here P of n, if we put this 1 here, so with P1, exactly 1 moves are required, right? So P of 1 here will represent that 1 move is required. So that is true. Then we move forward to the inductive step. Now in the inductive step, we assume that P of j is true for all j which are less than or equals to k, and consider that a puzzle with k plus 1 pieces. The final move must be the joining of 2 blocks, because that's what eventually the game is about. Of size z and k plus 1 minus j for some integer j with j less than j greater than or equal to 1 and less than equals to k. Okay. By the inductive hypothesis, it required j minus 1 moves construct the one block, and k plus 1 minus j minus 1 equals to k minus j moves to construct the other. Therefore, therefore 1 plus j minus 1.
Subtracting k plus 1 by, why are you saying k plus 1 minus j? Why are you subtracting them?
Over where?
Yeah, I said the final move must be the joining of two blocks of size j and k plus 1 minus j.
Yeah,
Why?
Yeah, so let me just finish this up, and I'll just give you a moment to ask your question. So 1 plus j minus 1 plus k minus j equals to k moves are required in all. So p of k plus 1 is true. Okay. So now here we have this p of n representing that be the statement that exactly n minus 1 moves are required to. So if it's an n piece puzzle, so we require an n minus 1 move to assemble a puzzle. Okay. So if it's only one piece puzzle, then we only require one move in the basis step. So that's trivially true, right? But if let's say it's greater than just one piece puzzle, so assume that P of j is true for all j which is less than or equal to k. So here we have a j piece puzzle in the inductive hypothesis. And then we consider that a puzzle with k plus 1 pieces, right? So here we have the final move must be the joining of two blocks of sizes j and k plus 1 minus j for some integer with with some integer which is j less than or equal, j less than or equal to k and greater than or equals to 1 as per the inductive hypothesis. So this is our hypothesis, okay? Now we did the inductive hypothesis step. So it requires j minus 1 moves to construct one block and k plus 1 minus j minus 1, which is k minus 1, k minus j moves to construct the other. And therefore, because we have proved that it requires k moves required for p, a puzzle of size p of k plus 1. Therefore, we have to prove this inductive step. Okay, let's take another example. Okay, so this is going to be the question number 25. So suppose that p of n is a propositional function, determine for which positive integer n the statement p and must be true and justify your answer. If p1 is true for all positive integer n, if pn is true, then p of n plus 2 is also true. So here, let's do that. So here we know that p1 is true for all positive integers n. If pn is true, then p of n plus 2 is true. Now, so p of 1 is true, we already know that. So in the inductive step, here allows us to conclude that p of 2 p of 3, because it's n plus 2, right? So it's p of 3, and then we have a p of 5, and then we have P of 7, and then we have P of 9, and then we have so many of them. So are all true because we have this here, right? But we can conclude nothing about P of 2 as per the question. P of 4, are they true or not? And then for the even ones, P of 6, and then P of 8. So we don't know anything about it. So therefore it's not a function, because we can say that we know P of 3, these ones are all true based on the question, right? So it's n plus 2, right? So we have this P of 1 is true, and then we keep adding 2 to 1, and then we start getting these ones. So we know that these are true because it says if P1 is true, then P of n plus 2 is true. But we don't know if what about these numbers? Are they true or are they false? Therefore, we cannot consider it a function. Okay. Now we will take another part. Let's take part number C, maybe. Now the inductive step here enables us to conclude. So here we have P1 is true for all integer, and if P of n is true, then P of 2 to the n is true. So here we will say that the inductive step here enables us to conclude that P of 2, right, and then it will be P of 2n, which will be 4, and then P of 8, and then we have P of 16, and likewise, are all true, but we can conclude nothing about P of n where n is not a power of 2. So for example, when it's P of 3, we don't know about P of 3. For example, P of 3, P of 3, P of 5. Anything other than these numbers over here, we don't know anything about it. Therefore, we cannot conclude that this is true or not. So therefore, this is not correct. Okay, this one was not that hard compared to the previous questions. So let's take, so this covers our exercise for 5.2 because we are not covering.
Hey, hold on. Leave the page there for a second.
I'm sorry?
I don't understand the last answer.
Sorry?
Yeah, okay. I get it now. Thank you.
Yeah, so basically what we did here is, so we have this assumption over here, and then we are saying that P of n is a propositional function. So it has to be defined for all the values, right? But it's not defined for these values and neither defined for these values. Therefore, we don't know. So this is not a function because it's not defined for, you know, some of the values. So function has to be defined for all the values. It cannot be undefined for some.
Right, right. Yeah, okay.
Okay. All right, let's move on to the next exercise. This is exercise 5.3 and page 378 of your textbook. Okay, take the first question. So in this question, in this exercise, we have the recursive functions. So recursive functions, I hope that you already know that what a recursive function is. But just to sum it up, a recursive function is when you start from something big, but then you have a basic step inside that function, and then once you reach that basic step, we basically kept recalling that function until it reached the very basic step to which you know the answer. And then after you get that answer, you start basically recursively coming backwards until you get the answer for the bigger part. So let's take this, have a look at this in action. So we have find f of n, f of 1, f of 2, 3, and 4 is defined recursively. So here we have f of n plus 1, which is defined in terms of n, right? So we have a function which is basically defined in terms of n. So this is a recursive function. So let's take this function. So we have this f of n plus, so let's take the part A. So for f1, this function, so we have this f1, which will be equals to, so if we replace this n here with 1, right? So we know that, so 1 plus 1, so n is 1 basically, over here n is 1. So is equals to f of 1 plus 2, right? So we know that f of 2 equals to f of 1 plus 2, right? But we already know what this f of 1 is here. Oh, sorry, f of what is it called? F of 0 here. So we know that f of 0 is 1, right? So let's take so here this will make f2 equals to f of 1 plus 2, but we want to know for f of 1, right? So this here, we don't know f of what f of 1 is, so therefore we will need to find the value for n equals to 0, right? So here what we will do is f of, so we'll take n equals to 0 here, so let me just say n equals to 1 here, and then we will say here n equals to 2 here. So here for n equals to 2, we have n, oh sorry, n equals to 0. So here we have 0 plus 1. So just putting 0 here. This is equals to f of 0 plus 2. Okay. So f of 0 plus 1 is f of 1. And then f of 0, we know this value because it's here. So f of 0 equals to 1. So we can just put 1 here plus 2. This is equals to 3. So now f of 1 is equals to 3. So we know that f of 1 equals to 3. So we find this f of 1 equals to 3. Now because we know that f1 equals to 3, we can also know what f of 2 is, right? So we have this f of 1 as 3 here. So we put 3 plus 2 to get 5. So we know that f of 2 equals to 5 here. Okay. Likewise, let's do for f of 3 and f of 4. So in order to make it f of 3, I will say f of 2, where, and let me just put this here. And then here our n is equals to 2. So f of 2 plus 1, which is equals to f of 2 plus 2, right? So f of 3 here will be equals to f of 2. We already found f of 2 is equals to 5 here, so we'll just put 5 plus 2, which is equals to 7. And then we will just do for n equals to 3 here. So f of 3 plus 1 equals to f of 3 plus 2. So f of 4 here equals 2. F of 3, which is 7 here. So 7 plus 2, which is equals to 9. So here, as you can see a pattern here. So we have to start from the where. So in order to find, let's say, f of 4, I have to know what f of 3 is. And in order to find f of 3, I need to know f of 2. And then for f of 2, I need f of 1, right? But the basic step of value, we know what it is. And then this is f of 0 equals to 1, which is the basic step. So we got the value for f of 0. We plug it in to find f of 1. And then we plug that in f of 2. F3 and F4, so it's kind of recursively finding the value. So this is why it's called recursive function. Okay, so we find f of 1, we find f of 2, f of 3, and f of 4 likewise. So this is as you can see a pattern here. So this is a odd series or an odd sequence, you can say. Odd number sequence. Any questions? Okay, so likewise, the other parts can be done likewise as well, because due to the limitation of time, I won't be going in that. So if anyone of you have a specific question, you can ask me through the email, but ask me beforehand. So this is the recursive function. Let's move on to the next question. So this is the question number 5. So we have to determine whether each of these proposed definitions is a valid recursive definition of a function f from the set of non-negative integers to the set of integers. So we have this domain. So from the set of non-negative integers, and then we have this range to the set of integers. So if f is well defined, find a formula for f of n, which when n is non-negative, and prove that your formula is valid. Okay, so let's take maybe let's take part number B. So here, so in part number B, we have f of n. Here is here f of n. So because we know that the range of this is a non-negative integer, and then the domain is the non-negative integer, and the range is the set of integers here. And then we know that it's for n greater than or equals to 1. So here f of n equals to, therefore, 1 minus n. This is stuff. So we we have the f of 0 equals to 1 equals to 1 minus 0. So we have this 1 equals to 1 minus 0 equals to 1. So it's true. So our basic step is true. Then we have this inductive step. So if f of k equals to 1 minus k, then f of k plus 1 equals to f of k minus 1
Well, miss.
equals to 1 minus k minus
N minus 1.
1 minus k plus 1. So let me just see it here. K equals to f of 1, which is equals to here, is equals to this one. Okay, so we start with the basic step, and then we take the n. So we know that n is here, n is where is that? Non-negative integer. So we start, therefore we start with the smallest one, and then we find out that it's true for the basic step. And then we take the inductive step for f of k, which is equals to 1 minus k, and then we have to prove for f of k plus 1 here, right? And then we did for f of k plus 1, we find out that it's basically 1 minus here. This thing here, if you will see the resemblance, is almost the same thing, but just for the next step. Therefore, this proves the inductive step and hence completes the proof. Let's take another question. So we have f be the function such that f of n is the sum of the first n positive integer. Give a recursive definition of f of n. So we have to here define a recursive function f of n, which will basically represent the the sum of the first n positive integers. So we have to construct such a function here. So here, if I say f of 0, so 0 here, so it will represent the sum of first 0 positive number. So sum of first 0 positive number, so which will be of course 0. So we know the definition of f of 0. So for f of 1 here, so for f of 1, we know that it will be 1 as well, right? So the sum of first positive integers. So 1 will be 1, and likewise we can do for the sum of first positive integers. Okay. Now we have to construct a formula. So we know that our basic or the minimal step is f of 0 equals to 0. Okay. So when the n is 0, then it will return us this 0. Yeah. So f of n here represents such a recursive function which returns the sum of the first n positive integers. So here f of n, if I take this f of n equals to f of n minus 1 plus n. For n greater than equal to 1, and it's important to define the domain because this works only for the positive integers, right, greater than 1. So now we have defined such a function. So if I put, let's say, for f of 1 here, I assume here n equals to 1. So here I replace n with 1, so it becomes equals to f of 1 minus 1, which is 1 minus 1 plus 1, which is equals to f of 0 plus 1, right, which is equals to f of 0. We know that it's equals to 0, so therefore it's equals to 0 plus 1, which is equals to 1. So here we know that this is actually true because the first positive positive integer sum is basically just the 1 itself. And likewise we can do for n equals to 2, n equals to 3, 4, and so on, using this recursive function here. Okay, let's take another example. So we have to prove this here. F of 1, f1 plus f3 plus f2n minus 1 equals to f of 2n, where n is a positive integer here. So we have to prove this. We can prove this using the inductive hypothesis as well. So just like any other proof, we'll assume what P of n represent. So let P of n be this thing over here, f of 1 plus f3 plus, so I can just word it like this, f of 1 plus f of 3 plus f of 2n minus 1. 2n minus 1, which is equals to f of 2n. Okay, so we are basically representing this Pn just like this here. I'm just writing it this way, okay? So it basically represents this here. Okay, so now we have the Pn representation, and then we will define the basis step. So what's going to be the basis step? So we know that P1 is true because f of 1 equals to 1, which is equals to f of 2. And then inductive step, we'll say assume that f of 0 multiplied by f of 1 plus f of 1 multiplied by f of 2 is equals to 0 dot 0, because we have said that f of 0 is 0. Then 0 multiplied f of 1 is 1. Then we have this 1 multiplied by 1, because our f1 and f2 are 1 and 1 respectively. So therefore it's this one over here, and which is basically equals to our as you here so we are assuming that here P of k, sorry, so we are assuming that here P of k is true. So we are assuming whatever we have here, it's true. And then we have to prove for P of k plus 1, right? So which will be f of 1, f of 1, f of 1 plus f of 3, f of 3 plus f of 2k minus 1 plus f of 2k plus 1 is equals to f of 2k plus f of 2k plus 1, because that will be the next number in the series, which is equals to f of 2k plus 2 plus f of 2 times k plus 1. Just factoring out 2 from here to get the 2 out. Therefore, our inductive step is true and hence true. Okay, so our Pn represents this statement over here, this equation over here, and then we did the basic step on this. So the n is a positive integer, so we'll take the first positive integer, and then we found out that it is actually equals to 1, right? And so is that f of 2 here. So here we did the inductive step in which we prove, we assume that p of k is true, and then we have to prove for p of k plus 1. So we take this f of 1 plus f of 3 and this whole equation in terms of k, right? And then we define this extra step which represents the k plus 1, the next number in the series. And then we have to add this respectively on the right hand side to make it balanced equation. Now that we have added this, so we can reword it like this here. Okay, now this one here, this is actually an equal sign here. So here, this one here, this form here resembles the one over here that we assumed, but just with the k plus 1, which we have just proved in the next step. So therefore, we know that our inductive step is true. Okay, let's take last question. So we have this recursive we have to define the recursive definition for this set of even integers here. So let's do part number A. So here we have this set of even integers, and then we have to give the recursive definition for the set of even integers. So here we have this this 0, which belongs to S, where S is a set of even integers. Okay, so we have this 0. We know that 0 belongs to this set of even integers. And if x, so we take any x, right? X belongs to S, then x plus 2 also belongs to S, because if you add 2 to something, so for example, if x is equals to 2, right, and therefore it belongs to S because it's a set of even integers. And therefore we know that any S x, which I create just by adding 2, it should also be in S because it will be an even number and it has to be in the set of the even numbers. So, and belongs to S, and x minus 2 also belongs to S, because if x belongs there, then x of minus 2 will also belong there. So this is a recursive definition of S. So if I want to, let's say, know, for example, does let's say 8, or maybe let's say 6 belongs to S, which is a set of even integers, then what we will say, okay, so we will go back to S minus 2. So here our x is, let's say, x equals to 6, right? So we will say, does x minus 2, which is equals to 6 minus 2, which is equals to 4, belongs to S? But we don't know if it belongs there or not. So we go further one step. So we will ask this, does x minus 2 minus 2, which is 6 minus 2 minus 2, which is 4 minus 2, which is equals to 2, does it belongs to S? But we don't know even does if 2 belongs to S or not. So we get down further one step. So here we will say x minus 2 minus 2, so 6 minus 2 minus 2, and then 4 minus 2 minus 2 here, and then 2 minus 2 equals to 0. So we'll ask if 0 belongs to S or not. We'll just put in question mark, belongs to S or not. But we have know that 0 belongs to S here already. So therefore we will say yes. So we know the answer to this yes, right? Now this question here depends on this answer. So now I can recursively go back there and put this yes here. So now, because we know that if I add 2 to it, it will still be, so it's a 0. So if it's 0 belongs to the set S, then 0 plus 2, which is 2, it will also belongs to S, right? So therefore 2 belongs there, and then because I know 2 belongs there, so I will check, does 4 belongs there or not? Because if I add 2, right, so if I add 2 to 2, so it will become 4, and then we know that it also belongs to S. So I know that this also belongs here. And then finally coming here, we know that 6 will also belong to S for the same reasoning. Okay, so this is kind of a recursive definition for that set of integers. Okay, question?
Yeah. So where can I find the recordings for the tutorials?
Recording for the tutorials, it should be actually on Microsoft Streams. So where you will usually find the lectures, you will find the tutorials recording over there as well.
Okay, thank you.
Yeah, and I will also be uploading the notes. I have already uploaded all the notes I've been taking during the tutorial. So if you want to refer to the notes, you can check it on Moodle as well. Okay, any other questions?
Miss, in an exam, I'm just asking, in an exam, let's say we have like a proof from 1.8, 2.1, 2.2. Will it be clear in the question which one we should do? Or we should just know which one to use?
So it depends. So like right now we have learned a couple of proofs, right? So it depends on the kind of question. So in some of the questions, so for example here, some of them we did, it says clearly to use, for example, the inductive hypothesis, right? So if I, for example, pull up some question here, so use strong induction, for example, it mentions here clearly, right? And then likewise, it can mention for the other ones too, like for example, in the inductive hypothesis using mathematical induction. So the one way is like in the question, you can be asked to use some particular proof, which could be the mathematical induction. But because mathematical induction is a little longer and is not suited for all kind of proofs, so therefore it's likely that you have to use some sort of other proof which might not be asked in the question.
Oh, okay, no problem. No.
Okay, so let's do a last part here. So let's do part number C. Okay, so we have the set of positive integers which are not divisible by 5. We have to give a recursive definition for that. So here, so we have 1, right? So we define the basic set. So 1 belongs to S. For example, S, let S be the, where S is the set of integers divisible by 5. Okay, so because 1 is not divisible by 5, right? So therefore it has to be in this set, right? And it's positive as well. Okay, so here we know that 1 belongs to S here. Now we have defined our the least the smallest possible set, and then we have 2. We also know that 2 belongs to S, right? We know that 3 belongs to S because none of them are divisible by 5. We also know that 4 belongs to S because this one is not divisible by 5 either. Now we know that 5 doesn't belong there because 5 is actually divisible by 5. Is a set of sorry, it's a set of not divisible by 5. Okay, so here we know that 5 doesn't belong there because it's actually divisible by 5, right? Therefore it doesn't belong there. But these 1, because it's not divisible, has to be in S. 2, 3, and 4 likewise have to be in S. Now if X here X belongs to S, then we know that X plus 5 we know that X plus 5 here also belongs to S, because let's say if it's 1, right, and then we know that 1 belongs to S, then for the same reasoning we can say, using this if statement over here conditional, we can also know that 6 also belongs to S, right? And because we know 2 belongs to S, we can know 7 belongs to S, and then likewise we can know. So this is kind of recursively. So just like the reasoning how we did here, we can do the same thing for example, if I want to know does 11 belongs to S or not. So this one here can be done using this recursive definition that we have found here. So in order to do this, so we can ask, so does, we can say, so does 11 minus 5, 11 minus 5, which is equals to 6, belongs to S or not? We don't know, because we only know that 1 belong to S, 2 belong to S, 3 belong to S, and 4 belong to S. We only know these ones belong to S, but we don't know about 6. Does it belong to S or not? So we go one step more down. So we say, does 6 minus 5 belongs to S? 6 minus 5, which is equals to 1, belongs to S. So now this 1 here, we know that 1 here belongs to S, so therefore we know that yes, it belongs to S. So here, therefore, we know the answer to this. Now we also know the answer to this, because we know that 1 belongs to S, and here, according to this one here, so if I add 5 to 1, we get 6. Therefore, 6 must belong to S as well, right? So we know that this belongs to S. Now, coming back to the main question asked, does 11 belongs to S or not? So we know that 6 belongs to S, right? And then 6 plus 5 also belongs to S, therefore. So here, 6 plus 5, 11 equals to, so therefore 11 must also belong to S. So this is how we write the recursive definitions for these statements over here. Okay, any questions here? Okay, if no questions here, then that'll be it for this tutorial. I will be uploading the recording on Microsoft Streams, and also these notes will go to the Moodle. So if anyone wants to check them out, so feel free to do that. And I'll see you guys in the next tutorial. Okay. All right, bye everyone. I'll see you guys in the next tutorial. Bye.
Bye.